Hello everybody. Today we're going to take another look at a type of problem you can solve using infinite series. This is not a geometric series. This is rather a Maclaurin series, which is a way to approximate pretty much any function with a polynomial. So let's get right into it. Using the methods of this section, find the first few terms of the Maclaurin series for the following function. Find the general term and write the series in summation form. And use a computer to plot the function and several approximating partial sums of this series. And here's our function here. I'm going to rewrite this so that it's more useful to us. We have the 1 plus x on the top. We have the 1 minus x on the bottom. And remember your logarithm rules. Nobody remembers logarithm rules, but they come in very handy in this situation. You can solve the problem without them, but it's way a lot more work. So a division inside a logarithm can be made into a subtraction outside of the logarithm. Which, like I said, comes in very handy, this problem. But in general, it's a good idea to remember that anyway. So this equation, 13.4, looks like a good candidate to use for this problem. We have this here exactly matches the left side of the equation in 13.4. And this, while it's not quite the same, we can change it around to make it work. So the nice thing about these series is that you can add them and subtract them, and they still, since they're equal, it leaves it equivalent. So we'll start out here. I'll just rewrite it, and we'll get right into it. Though I am going to be a little sneaky here when I rewrite this. So this is 1 plus y, and I'm defining y to be negative x. And this is so that it will exactly match this form up here. We just have to remember to resubstitute later. And since they're all equal, exactly equal, this will still work out correctly. So we have x minus x squared over 2 plus x cubed over 3. And it says the first few terms, so we'll stop here for now, even though that would go on forever. And we have our minus here. And remember, this is y now, because y is our variable there. But other than that, it's the same. Well, it'll be the same if I write it correctly. And remember what was just coming out of my mouth while I was saying that. So once again, this goes off infinitely, but we don't need to worry about that. So I'm going to simplify and substitute back for our y here. And I will, remember we're subtracting here, but this is a negative x because it used to be a y. And then this is a negative here, so that's positive. But then once again, the negative in our negative x up here is taken care of by the square. Just remember to write that square in there. And then, yeah, this is subtracted, that's added, so that's subtracted. Then we have a triple negative on top from that, which means it ends up being negative. And this goes on forever. So when we rewrite that, we find that these are positive, double positives, because they're double negatives. And then this term cancels with this term. So what we have is this original function equals 2x plus, and we have 2 of these also, 2x cubed over 3. And I did these calculations before, and since some of our terms canceled out, we'll write another one here. This is the next term in the series. The x to the fourths would cancel out, and we would end up with this, and this series goes on forever. So these are the first few terms of the Maclaurin series for that function. The general term, we got to remember our definition of even and odd numbers here. So our general term is 2 times x to the, so yeah, our term n is 2n plus 1 over 2n plus 1. Because those are all the odd numbers. The series in summation form is just the same thing, but you got to remember where to start. We're starting with n equals 0 because our first term is an x to the 1 over 1. And it does go off to infinity. 2x to the 2n plus 1 over 2n plus 1. So these are our answers here. Now for part C, use a computer to plot the function and several approximating partial sums of this series. Here's what we have for that. So this here is our original function, and these are all progressively getting closer and closer to the function, as you can see. Once again, these are only valid between -1 and 1, because that's where they converge. Now, for how to solve the problem if you don't remember your logarithm rules, you can use 13.4 here, but it's a lot more complicated. You can rewrite this function as ln, here, I'll make that a bracket, 1 plus x, 1 minus x to the -1. And remember, since they're all equal, you can multiply series together also. So you end up with this times the series created from this and 13.5. It's very messy, but what you end up with is that that's equal to ln of 1 plus 2x plus 2x squared plus 2x cubed. And that goes on forever also. So this is another exactly equal approximation using infinite series. It's not a Maclaurin series because it's not solely a polynomial. The polynomial is inside the logarithm. But then using that and this 13.4, there's a way to rewrite it so you get the same answer. But you have to deal with, not only do you have an infinite series, you have infinite series, because you're plugging an infinite series in for each one of these. So the approximation it gives, I just realized I haven't been sharing this part of the screen. So yes, what I did was this here. You can rewrite it like this, and then that ends up with this infinite series here, this infinite series. So this gives an approximation that looks like this, where this is the original function, and these are getting successively closer to the series. It's a worse approximation, and it takes way more effort, So the moral of this is remember your logarithm rules. Thanks for watching.